Recording is rolling for today's Wednesday, October 20th. Here's our agenda. Top scientists. Yeah, I do have to show you guys the top scientists list. So this is the last quiz you guys just did that you just turned in a couple days back. If your name's up here, then you did super awesome. I always have so many top scientists in this class. So yeah, way to go. Good job. You guys are doing awesome. Because you guys know that I give you guys some hard quiz questions. You guys get some pretty tough quizzes, but you guys are doing awesome on those. It's not because I'm asking easy questions. So yeah, definitely way to go. So, well, I did the hydraulic jump already in a separate video. The top scientists. So we're going to take the rest of class to do this conservation of energy table. We do right here. We did the first two rows yesterday, so you guys get the gist of what we're doing. There's some scenario. We got to identify the objects in the system. I said closed system, but talk about that. Okay. What's the energy at point A, the energy at point B, and if energy is conserved, those must equate. And then you can solve for stuff. For example, what's the final speed? Might be a pretty classic question. Here's all your building blocks of energy. Well, the ones that we care about, mechanical energy forms. So we're just going to shop from this list. All right. Next scenario, a kid slides down a hill length L and there is friction. Okay. What objects, what objects do you think are going to be relevant to the system? I think that the kid in the sled, I'm going to treat as like one object, kid and sled. Right? Also, the fact that there's a height change means that you got to include the earth. Because the Earth is pulling with a gravity force, like an external force, right?
Where did you get sled
Yeah.
from? Threw it in there.
The what?
You said kid and sled.
Yeah, the kid and sled is like one giant object from a physics point of view. Right? They're all just moving together. The kid and the sled.
Who says he has a sled?
And then the fact that there's friction. Here's what I'm gonna do. I know I said open system for these, closed system. But for this one, make this note. Call this an open system, consisting of only the kit sled and the Earth, right? But we're going to make this an open system, meaning that the external force, in this case, the friction force, is, doing negative work on the system. Can you rephrase that? And so what kind of energy at point A? Has a height? Yeah, potential energy, mgh at point A. Okay. By the time you get down to point B, well, you'd have to be in motion to get down there, so you're probably moving. So do you think you have some kinetic at point B? Yeah, there's some 1/2 mv squared at point B. The m, of course, refers to the kid and the sled together. And if there was no friction, wouldn't that be it? This kind of energy turns into this kind of energy? Yeah. And wouldn't that be exactly the same setup as the Galileo question? And doesn't that also mean that you'll end up with the same speed at point B? Maybe I should have asked you guys that before we started on this thing. The fact that this is an incline, would the speed at point B be more than, less than, or the same as if you just dropped it straight vertically? But I sort of just led you guys straight to the answer. Isn't the speed at point B the same as if you just dropped it vertically, assuming no friction? That's interesting. It doesn't matter how long this incline is, or if it's maybe like a 1 degree angle and it just falls for miles or something. Right? If there's no friction, like air hockey table, it's just the same result as Galileo dropping the ball. Right? But there is friction. So as an open system, we're going to say that, I'll do this, like minus work due to friction. Right? The friction did like negative work on the system. Think of it that way. Okay. All right, so let's set up a conservation equation and figure this out. Okay. So there's only going to be 2 examples like this on this whole page that I'm going to do this. The sum of energy at point A. Now, yesterday I said equals sum of energy at point B. And for a closed system, that would be true. But for an open system, I'll say this, minus the work done by friction leaves you with whatever energy is left over at point B. Okay? Sum of energy at point A minus work done by friction is equal to the energy left over at point B. Right? So for an open system. Okay? This is a work energy theorem. Right? The work you do on something is equal to the change in energy. At point A, it was all mgh. Work done by friction, isn't that force of friction times the distance, which is length L? It's kind of like I just chopped this expression right here. Work is force times distance. And the distance is specifically the length of the slide, isn't it? And that will leave you with whatever's left over is going to go into kinetic at point B, isn't it? You see that? Okay. Now, you guys good so far? Okay. Now here's where, if I wanted to just focus on the big picture things, I would just multiply both sides by 2, divide by m, take the square root, and then get dB in terms of these other variables. Okay, fine, whatever, move on. Okay. But since you guys are AP, let's go a few layers deeper because you never know exactly what question's going to be thrown at you. So let's see how far we could take this question. Because friction force, isn't that coefficient of friction times normal force? Okay. Before you get rolling too far, I wonder, do you guys think the mass might cancel out at some point?
Yes.
I see 3 terms, mass is in 2 of them. I wonder if mass has something to do with this friction force and might eventually cancel out. Let's find out. Okay. So let's go on this quest, just for you guys since you're AP. Coefficient of friction times normal force. That's subbed in for friction force. Okay, times the length. It's 1/2 mv squared. Normal force. For anything on an incline, walk on an incline, what's normal force equivalent to? Mg times mg cosine theta. Yeah. Guys remember that's mg cosine theta? Okay. That refers to this theta, whatever that theta is, times L equals 1/2 mvv squared. Okay. Like that. Okay. So does mass cancel out? Yes, it does, because we have 3 terms, point, 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 and they all have m in them. So if you suspected mass was going to cancel out anyway, then yeah, great. Maybe this kid has a friend who has a different weight and in the same type sled. They sled down together. They're going to move side by side all the way down. That's what that means. So multiply both sides by 2, take the square root. Looks like v point B, based on, well, this set of variables would be, let's see, I need times 2. So 2 GHA minus 2 mu g cosine theta times L. Okay. That's one possible correct way to write that, I think, unless I made a mistake, but that looks pretty good, right? Okay. There's another layer you could go deeper, which is, notice I never gave you the theta to start out with, but I did give you maybe height and length. Hey, height, length, and theta, those 3 are related to each other, right? Could you say, you could probably sub out theta in terms of H and L. You could do that. Okay. Maybe I'll just leave that there. Okay, there would be a way you could get cosine theta in terms of H and L, but it's a bunch of geometry. I don't want to get too far into the woods. Okay. So that's this box right here. Square root 2GHA minus 2 mu g cosine theta times L. Big old expression. Okay. And then last thing I want to say about this though is, okay, so we set up conservation of energy, did the algebra, chug, got the answer, all fine and good. Okay. Make sure you can read the music of the equation, what's communicating to you, make sure that makes sense. For example, what if there was 0 friction, coefficient of friction is 0, like air hockey table? Wouldn't this term go away? And look what you would get. Speed is equal to square root 2gh, just like the Galileo problem. Okay? And then if there is friction, well, you'd be subtracting a term. Okay, so that makes sense too, right? And car brakes to a stop. Hey, we've seen the story before. Car brakes to a stop. So, see where we're going with this. So, what objects in the system? There's the car, right? Because the object is changing speed. Okay. You could argue that's the only object in the system. Do you want to include the Earth? That's kind of a gray area. I'm going to leave that out because the Earth is providing a force in the car, but it's canceled out by the normal force. So there's no height change. So I'm going to leave the Earth off. Okay. I'm also going to, this is the other one that's also an open system. Because for the car brake to stop, there must be friction. So I'm going to say a system that includes only the car. See if I incorporated the road, maybe I could argue that would be a closed system, but let's do it this way. Okay. So the car starts off with what kind of energy at point A? Kinetic. Okay. Kinetic. Okay. I mean, there's only a handful of types of energy, so I mean, these are all our options, right? So this one right here. Okay. And by the time the car comes to a complete stop, does it have any kinetic? No. Has it rolled up any hills to come to a stop? No, so no potential. I don't see any springs. So how much mechanical energy at the very end? Zero. Okay. And the same idea as before. The only way to get there is because there was negative work being done on the car by the friction force. So something like that. Okay. So this is the only two open systems on this whole table are just these two here. Okay. So the sum of energy at point A minus the work done by friction in this case leaves you with the sum of energy at point B, which happens to be 0 joules. So we got our 1/2 mb at point A squared minus, now work done by friction. Isn't that friction force times stopping distance, x? That leaves you with 0 joules of energy, like that. That'd be a good setup, right? You guys could probably do that on your own too. Okay, let's go ahead and just answer this last box question before I go where I really want to go with this question. What is the speed of the car at point B? 0. Boom, done. Okay. The question that's actually the more relevant question for this one is, what's the braking distance? Can you solve for that x? Okay. Let's do the whole thing where we sub out the friction force with coefficient of friction times normal force, all that stuff. Okay. And coefficient of friction times normal force, well, for a car on a level road, what's the normal force equivalent to?
mg.
Yeah, its own weight. So there's your friction force, u times normal force. Okay. So times braking distance, okay, that's a 0 out. Okay. Okay, so if you're solving for x, you've got to do some, slide these terms around with algebra. So mu mgx is equal to 1/2 m times starting speed squared. Oh, what's going to cancel out? The mass of the car. In fact, remember last time I told you the story? The mass of the car also canceled out. This is a really classic physics question. If you have a little sports car and a big old semi truck side by side, all is equal, same road, same tires, same starting speed, they both hit the brakes same time. They both take the same stopping distance before you come to a stop because mass cancels out. So then stopping distance is equal to, what do we got here? We've got a VA squared, the starting speed squared, divide by 2, divide down coefficient of friction and gravity field. Okay. That wasn't the question on the table, but that's the question that, well, I want to take another look at this. Right, so see if you can read the music of this equation. If the friction, coefficient of friction is increased, what does that do to the braking distance? Decreases it. There's an inverse relationship, isn't it? That makes sense. More friction, less stopping distance. Okay. What if you sped up the car faster, faster, faster? What would happen to the braking distance? Gets increased. What if you specifically doubled the initial speed of the car? What would happen to the braking distance? And it doesn't double. Quadruples. What if you triple the initial speed of the car? What happens to the braking distance? 9 times. Which is a story that you guys have seen before in this class, just from a different point of view. And I'll show you guys it's the same thing too. Right? If you have trouble with that, here's a trick I show my honor students is if this equation is true in general with just variables, it should be true for any specific case. For example, what if the car was going at 1 meter per second and there was a coefficient of friction of 1/2 and there was a gravity field, let's say it's a little tiny moon somewhere with 1 meter per second squared. Right? What would the stopping distance be on that car? 1 meter. It would take 1 meter for all those numbers to play out. Okay. But what if you triple the speed of the car to 3 meters per second and everything else is the same? Same coefficient of friction, same planet with really weak gravity. Now what's the stopping distance of the car? Yeah, 9 meters. So tripling speed, stopping distance goes up by factor 9. Okay. Now let's compare this to the old way that we used to think about this, the old way we solved this problem of stopping distance. The way we used to do it was this. We just set up a free body diagram for the car. Said this, let's have this car traveling to the right, some V naught. Okay. There was a weight of the car, there was a normal force from the road, which was equivalent to the weight. Okay. And then there was a friction force. And that friction force, I need to give myself enough room. Okay. That friction force is equal to coefficient of friction times normal force, which is equal to coefficient of friction times the weight. You guys remember that whole expression? Okay. No, I got that crammed in the corner so I can do some more work out here. Newton's second law of motion says acceleration is net force divided by mass. which is, hey, isn't the net force the friction force, which is this expression right here? Mu mg divided by mass of the car. Okay, so the rate that the car can slow down is mu g, coefficient of friction times the gravity field of the planet. Okay. Now that's just the rate it can slow down. But if you want stopping distance, you have to go back to kinematic motion, set up a tax VV table, and say, okay, well, here's the slow down rate of the car. We're solving for stopping distance, so the rate it can slow down is mu g. I'll make that negative just because slow down. Okay. The initial speed of the car is whatever it is. And there's one more thing you have to know. What's the last thing you know? Final speed is 0. That's 3 things. And if you're solving for that x, then which of these 3 amigos is going to get you there the fastest? The third one, the one that doesn't deal with time. Exactly. The third one is most closely related to what we're studying anyway, conservation of energy. Df squared equals v naught squared plus 2ax. Okay. So 0 equals v naught squared, plus 2 negative mu g x. Okay. So 2 mu g x equals initial speed squared. Divide both sides by 2 mu g, and the braking distance equals v naught squared over 2 mu g. This was the old way that we used to do it. Okay. Look at everything you have to do. Free body diagram, find the net force, do a bunch of subs, go route that into doing second law motion, solve for the acceleration, then take that acceleration, go back a previous unit to kinematic motion, shop for equations, plug it in, and finally you can get the braking distance. Whew, that was a long journey. But look at this new way of doing it. This energy equals this energy. Boom, 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 done. It's the exact same answer. You guys got it? So a lot of times conservation of energy will get you, will solve stuff faster. A lot of times that's the case. This next one. This next one I really should have made a poster for, but yeah. The spring fires a block into this frictionless track. Ooh, think of this as frictionless because that's easy to create a closed system. Right? What objects do you think are in a closed system? There are 3. What's one of them? The block. There's also the earth. Yep, the earth and the spring. You guys got them. Block, earth, and the spring. That's it. Now you might argue, well, what about the track? Isn't the track pushing on the block? Yes, there's a force from the track on the block. That's the normal force. But the normal force, by definition, is always perpendicular to the motion. And remember, like moving a textbook horizontally across the room, there's no work associated with that. Right? So the track doesn't actually do any work on the block. What's the energy at point A when the block is spring-loaded? How about some 1/2 kx squared, the energy stored in the spring, right? Then you release it, goes, flies around that loop. At point B, what kind of energy at point B? There's 2, potential and kinetic, right? So some of the energy went into lifting the block against gravity. That's your mgh, sub B. And whatever's left over is left for its motion. And this block does have to have a speed at point B because the only way to get there in the first place, it had to go through this loop, so it had to have sufficient speed to do that. There is a 1/2 mv at point B squared. We can solve for that. So those 2 added together. Here's where the energy came from. Here's where it went to. Energy accounting, they must equate. No frictional losses. We're back to our old classic closed system. Sum of energy at point A is equal to sum of energy at point B. So got our 1/2 kx squared turns into mgh at point B plus 1/2 mv at point B squared. Let's solve for VB. We're done with the physics. Everything else is just algebra at this point. Oh, do you guys think the mass is going to cancel? How many guys say no? The mass is actually going to stay in the equation. Yeah, you're right, because this term has nothing to do with mass, does it? So mass can't cancel. Right? Probably makes sense anyway. Put a big old mass there. Like what if this was a golf ball versus if it's like a bowling ball? Do you think it's gonna play out differently? Yeah, it sure would, wouldn't it? All right, so subtract this term over, got 1/2 mvb squared equals 1/2 kx squared minus mgh. Way to interpret this particular line is whatever energy you started with, take away the energy to lift the block, you'll be left over with energy that goes into its motion. I'm going to do a double algebra step here. I'm going to multiply everything by 2 over m. That will distribute into each of those three terms. That'll be bb squared is equal to, okay, this is going to be kx squared on m minus 2gh. So b. Okay. And then finally, square root. And this is the answer. How fast is that block moving at point B? That's this right here. So that is, copy paste that right over here. bb equals square root kx squared on m minus 2gh. So it'd be just like that. Okay. Okay. Let's read the music of this equation. Make sure it checks out. Okay. So if you had a spring that was really stiff, had a huge k value, would that make it go faster by the time it gets to point B? Yes. What if you compress the spring even more? Yeah. What if you had started with a golf ball and then you replace that with a bowling ball, just to say you're increasing the mass? What does that do to the speed? Decreases it. In fact, the bowling ball might not even make it, right? What if you warp this trap so that you raise the height that it had to go to get to point B? What would that do to the speed? It would decrease it, wouldn't it? Hey, like you're subtracting that off. Ooh. See how that all kind of checks out? Makes sense. A bungee jumper dives off a platform and barely touches the ground before the cord retracts. I'll tell you guys what, there is an FRQ that I stole this scenario from. Now, the FRQ is a little bit more involved than what we're doing here. We're doing a simplified version of it. But yeah, this is an AP question right here, a past FRQ. Right. What objects in the system?
Ball.
Yeah.
Bungee jumper.
Yeah, the bungee jumper.
All right.
They did call him a diver on the FRQ too, and I've been using that word today, so yeah, just write diver. So the bungee jumper.
The cord.
The cord, you are right. The cord is, yes, the cord is important, and also the earth. Those are the three relevant objects. Yeah, the cord was a tricky one, but you guys got that, so that's awesome. Okay. Now, why does the cord matter? Well, maybe you know already. Oh yeah.
Air resistance would be part of this system.
Ah, yeah, that's a good point. So, what about air drag? Okay, now air drag we normally ignore in this class, and we'll do that here too. But if we did incorporate air drag, then you would have to consider that. You'd treat it kind of like friction, and you'd say then it would be probably an open system, and some of the energy would be lost to that. So, but let's just treat this as a closed system, no air drag. So, what kind of energy at the beginning? Potential energy. There's your mgh at point A. Okay. What kind of okay, so diver then dives, flying faster, 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 and then that bungee cord starts to stretch, and then you get to point B. See where it says he barely touches the ground? Maybe it's like there's a sidewalk down, and it says, right, and then just like touches the sidewalk, and then the cord retracts, pulls it back up. So at that very point, there's no more potential energy because you're at ground level. Is there kinetic energy? At point B. No, because you're turning around. Kind of like if you throw a ball straight up in the air at the top, it has 0 speed. So similar story here, except upside down. Right? It's turning around. If there's no potential, and there's no kinetic, where'd all the energy go? Into the into the cord, which we're treating as a spring. Yes, we're treating the cord as a spring. We're going to assume that the cord follows Hooke's law. Okay? So wouldn't that be, what's the expression for that? 1/2 kx squared, where x represents the amount that the cord stretches beyond its initial length, right? Is that true? That's the whole setup. Wait a minute. I thought that when the diver was falling faster, 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 wasn't he picking up kinetic energy? Why is there no kinetic energy in any of the setup?
Does the bungee cord undo that, basically.
Right, because it does eventually go into the core. Right? See, all I care about is point A and point B. That's what this is, point A and point B. Okay, now, in the middle, there was kinetic energy, but I don't care about the middle. All I care about is point A and point B, initial to final. So that's it. Yeah. So let's do the setup. The sum of energy at point A equals the sum of energy at point B. At point A, it's all mgh. At point B, it all goes into the bungee cord, 1/2 kx squared, where x represents the amount the cord was stretched. Oh, what's the speed at point B again?
0.
Okay, we're done with that one.
Yeah.
Next couple of problems. Hey, Atwood, here comes back Atwood. So I start with the modified Atwood because actually a little easier to solve, and then we'll go to the classic double elevator Atwood. Okay. Now, what is the speed after having moved some distance? Do you think you guys could solve this from past info, like dynamics and kinematics put together? You could, and I will show you guys just for the modified one that it ends up being the same thing as conservation of energy. Okay. But let's do conservation of energy. What objects are in the system? I'm looking for 3 objects.
The blocks.
Yeah, each of the blocks. Yep, you guys got them. Each of the blocks and the Earth. Nice. Right. The Earth you have to include because of that height change. Right. And there's a external force from the Earth that matters. Right. Oh, okay. Now here's where you have to expand your imagination a little bit. Right. What do you think? How should you set this up? What energy at point A? It is potential energy. Yeah, M2 is going to eventually fall some height x. I call that x. Is that true? Right? And that's supplying, the fact that M2 can fall and will fall, that's supplying the energy for the whole system to move, isn't it? Right? And by the time M2 falls that distance, let's define height 0 to be at point B. Right? And if you do that, then what's the energy mix at point B? Yeah, 1/2 m2v squared, and also, isn't that also dragging along m1? So plus 1/2 m1 dv squared. Right? Here's where the energy comes from. Here's where it goes to. It has to go into moving both blocks because they're tied together. Okay. All right, so let's solve this for VB, and then I'll show you guys how it's consistent with ways that you could already solve this from before, just like we did with the braking car. So sum of energy initial, or at point A, equals the sum of energy at point B. Okay. So we're starting off with all m2gx, because x is the height change, whatever I call it that. Okay. And that's going to go into 1/2 m1v squared plus 1/2 m2v squared. Okay. So go. I could factor out the vb squared just to consolidate that. I mean, we're done with the physics at this point, right? We're just doing some algebra for a while. Okay. So I got 1/2 sum of the masses times vb squared. I guess you could have thought about it like that from the start. The fact that those two masses are collectively tied together, so they'll always have the same speed. I mean, that probably makes sense, right? I guess you could have started there. Solve for vb. Well, multiply by 2, divide by the sum of the masses. So vb squared is 2 m2 gx, all divided by the sum of the masses. And then vb itself is just the square root of that. So copy paste that over here. vb equals big ol' square root. Okay, so last few steps were just algebra, but let's go back into a physics thought process again and think, okay, read the music of this equation. So that distance x, what if that block falls further? What's happening to the speed? It's increasing with the square root type relationship, is it? So if it falls 4 times as far, it's going to be going twice as fast. Right? Do you see sort of a square root 2gh buried in here? Square root 2gh? It almost is. In fact, it would be square root 2gh if hey, what if you did this? What if you took block 1 and set that equal to 0 kilograms? Like, if that's true, then wouldn't this be just like an empty string? And then would this just turn back into the Galileo problem? And all the m's would, because if this is 0, m2 over m2 cancels, square root 2gh. That is the Galileo problem, wouldn't it be? Right? So, okay, this checks out. This makes sense. We know we did it right. Okay? But I want to make sure we did it right. I want to go back to dynamics and kinematics. So the acceleration of the system is the net force, which is the hanging weight, divided by the total mass, which is m1 plus m2. Okay, so net force on total mass. Okay. Then let's do tax VV. Well, we know what equation it's going to feed into anyway, which is final velocity squared equals initial velocity squared plus 2ax. Okay, you guys remember that? Okay. Take this acceleration expression from Newton's second law of motion. Pop it in right there. This thing starts from rest. That goes away. And then whatever speed it's going to be, squared, equals, let's see, that's 2 times m2g on some of the masses, all times the height change. Okay. And then the final is just the square root of that, which looks like square root 2 m2gx on some of the masses. Oh, that is exactly what we got with conservation of energy. Okay. So here's the old way of doing it. Newton's second law, and then go back to kinematic motions and solve stuff. Here's the new way of doing it. This energy equals this energy. Boom, boom, boom. That's the same thing. Okay. Oh, yeah. If you're ever hung up on an AP question, or life in general, right? Sometimes a good thing to do is come back to it later. Sometimes you see things from a different perspective. But speaking of different perspectives, sometimes there are different approaches you can take that will lead you always to the right answer. So yeah, you just have more and more tools in your toolkit. Let's do the double elevator outward. Now this one we'll just do conservation of energy. Okay. This one's a little trickier. That's why I listed it second. So it's the same objects, right? M1, M2, and the Earth. Okay, so same objects. The tension in the string, that's just internal to the system. So ignore that one. What is the energy at point A? What do you guys think?
Is it just nothing?
Well, how about this? This system, it looks like it's going to probably move clockwise. Guess it? Clockwise? I guess M2 moves down, maybe M1 moves up, point A to point B, right? Kind of like before, it was sort of like this. Now it's like this. Okay. So the fact that M2 is falling, isn't that like losing potential energy, right? So it had to have had some potential energy to start with. Let's call point B height 0. That's what that dash line is about, too, the little dash line down there. Right? So isn't there some M2GH, just like before? Just like before, right? Okay, so that's what's supplying the energy from this point of view to make everything move. Okay. And then by the time these blocks move to point B, which is like this, one's going down, one's going up, where did the energy go? And I'm looking for 3 terms in this box. What's one of the terms? Looking for 3 things. Okay, so 1/2 mv squared for each of the blocks. So we got some 1/2 mv squared for block 2. We got some 1/2 mv squared for block 1. And it's the same speed because they're tied together with the string, so they're always moving the same speed. But there's one more place the energy goes. Exactly. The potential energy for the first block. Block 1 being lifted. Right? Isn't some of the energy diverted into block 1 being lifted? Right? There's some work done on that block to lift it. Okay. Here's where the energy came from. Here's where it went to. Is that okay? And then the only difference between this one and last one is, well, the last one, block 1 was moving horizontally, so it didn't need to be lifted. It just needed to be sped up. All right, let's go. Sum of, for you guys can see this. Sum of energy at point A is equivalent to sum of energy at point B, conservation of energy. At point A, it's all M2GH. Okay, so block B is going to fall at height H, and then that energy will be delivered to, well, three things. You got your 1/2 mv squared for block 1. You got your 1/2 mv squared for block 2. Solving for this VB. And then block 1 had to be lifted, so M1GH. I mean, whatever height M2 falls, M1 is being lifted to the exact same height. I have 4 terms. Right. Let me pull these two together and factor out the VB squared, and at the same time, I'm going to slide the M1GH over. See if you can stay a step ahead. See if you can beat me to the answer. Right, so let's have an algebra race. So I'm going to do 1/2 M1 plus M2 VB squared is equal to, I had an M2GH over there, but now I'm going to subtract over the M1GH. Like that. Then multiply both sides by 2. I could factor out a GH, too, couldn't I? So maybe like difference of masses, GH. Divide both sides by the sum of the masses. And finally, take the square root. That's the answer. There's that right here. VB equals, now this is the speed of each block. You could say the velocity of each block if you specify one's going down, one's going up. So 2, difference of masses, GH over sum of masses. Yeah, square root right there. Is that right? Okay, so what have we done with this problem so far? We've looked at it from an energy context. I won't do the whole kinematic thing and dynamics thing, but if you did it with that approach, you would get the same answer because it's been consistent so far. Right. We set up an energy conservation. We went chug with a bunch of algebra. We got the answer, and so great. We have an expression that will tell you how fast each block is moving as a function of each mass, the height change, and also the gravity field. And the last thing I want to do with this is to poke around with this formula and see, is this really consistent with everything else you know in physics so far? So, for example, let's think about boundary conditions. What if these blocks had the exact same mass? If they're the same mass, what's that system going to do? Nothing, right? It's just going to sit there, right? So you guys know that. You had about 200 grams, 200 grams. You guys tried this out in real life, right? Oh, look at that. If they're the same mass, doesn't this zero out? So there's like no speed, right? So there's that. What if you go the opposite extreme? What if you load all the weight onto one side? So M1 becomes 0. That's what that would be, right? If M1 goes to 0, okay? Let's see what would happen. If M1 is 0, that goes away, that goes away. Oh, would this simplify to, what is M2 over M2? If this is 0, this is 0. That goes to 1. So that would, hey, what's that simplify to? Square root 2GH, which is the Galileo problem again, isn't it? Which it should be if all the weight's on one side. Yeah. That's how fast it goes as a function of drop height. Yeah. Guys good? We're going to do 2 more scenarios because as far as I've been getting across today. So a spring fires a ball vertically to its maximum height. What's in the closed system? What do you guys think? The ball, the earth, and the spring. Ooh, good call. You guys got them all. Nailed them. What is the energy at point A?
1/2 kf.
Exactly, 1/2 kx squared. Right? 1/2 times the spring stiffness times the compression of the spring squared. Right? Some number of joules, right? So it's like spring loaded, ready to go. And then you let it go and it flies up to its maximum height. Right? And at its maximum height, what kind of energy does it have?
Potential.
Potential energy. Okay. Do you guys see any speeds anywhere? Is there any kinetic energy? not at point A and not at point B. Now, there was in the middle, but we don't care about the middle. Well, unless you did, you could set it up that way, but not at maximum height. Yeah, maximum height, there's no speed. So that's it. I could solve for dB. Oh, what's the answer to this question? 0. 0 meters per second. Is that? Do you guys think if you did here? Let's think of an experiment that you could do with this. There's you get you guys a lab on this at some point pretty soon. What if say you had an ink cartridge and this pen? I got the spring right here, spring loaded, right, and I aimed it straight upwards. And maybe I know the mass of this cartridge, right? And I know Earth gravity field, and I know how much I compress this down. Maybe it's about a centimeter or something like that. Right, now let's go. And it flies up to some height, and maybe I grab that height. If I know all that stuff, if I know the height it goes up to, the gravity field of Earth, the mass of this cartridge, right? And also the compression amount, maybe like a centimeter, something like that. What could I solve for?
Spring constant.
The spring constant. I could know how stiff that spring was to send it to that measured maximum height, right? Or if you already knew the spring constant, say like, oh, I know the spring constant of this model pen. Right? You could calculate ahead of time what the maximum height would be, couldn't you? Something like that. Just by equating these two terms and then solving for whatever, you can solve for whatever you want. I mean, there's like 5 variables floating around, so as long as you know 4 of them. Next question. A block falls from some height and squashes a spring. So isn't this problem just the exact same as we just did in reverse? Right, so it's going to look very similar. Right? Side note here, see in parentheses it says, assume no mechanical energy loss during collision. Okay. That is a really important detail for reasons that we haven't talked about yet in this class, having to do with conservation of momentum, which is the next topic we'll talk about. Whenever you see things colliding, you should immediately think conservation of momentum, which I know we haven't even talked about yet in this class. So that's why I had to mention that detail. So we're just going to ignore some of that stuff. Right? But it's the same objects, right? We've got the ball, the Earth, a spring, okay? Those objects. Okay? The energy at point A is what kind of energy? Potential energy. There's your MGH. Point A. And now if it squashes the spring, do you think what's probably going to happen is that spring's going to get squashed and then rebound and like fly that thing back into the air? Okay. And if there really was no energy loss, then ideally would this thing go like boing, 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 and just like do that for like thousands of years, right? Sure, if there was no energy loss, truly that's what we do, right? So let's look at the maximum spring compression. Right? That would be just 1/2 kx squared, wouldn't it? You have to fill in some details. I know you guys have really simplified scenarios for these things, but like assume with this, I know a good question. This x, right? What x does this represent? And I'll give you guys two options. Right? If this block was just at rest on the spring, it's going to compress it some amount. Right? Or if you drop it and it compresses it, it's going to compress a greater amount. Actually, I think it's being like twice as much. Right? I'll show you guys that later in the year why that is. Right? What does this x represent? Does it represent the maximum compression or the equilibrium compression if the block's just sitting there at rest? And you guys would say the maximum compression, because it's going to compress it as much as it can possibly compress it. Suppose it squashes it like 2 centimeters, and then the thing is, right? And then after a while, it eventually comes to rest. Right? So it's sitting in equilibrium. That equilibrium point, it only squashes about 1 centimeter, about half as much. Right? I'll prove that to you guys in the future. So that x would represent the maximum spring compression. Right? And what is the speed at that point? 0 meters per second, because there's no kinetic energy at that point. Okay. All right, so that is our wrap on class today.